In this video, we're going to look at ANOVA, known as analysis of variance. In a hypothesis test using ANOVA, we're testing for a difference in means across more than two categories or groups. So here we're looking at multiple means being equal versus at least one of them being different. And so today we'll look at the hypotheses, we'll look at measuring the variability both between groups and within groups. We'll look at the calculation of the F statistic and computing the p-value, as well as stating our conclusion and pulling together the common ANOVA table that is generated from software. So basically, for any hypothesis test, we usually go through the 4 steps: state the hypotheses, calculate the test statistic. In this case, the test statistic is called the F statistic. We'll compute the p-value and state our conclusion. For ANOVA, it's important to know that we've got 3 assumptions. So the first, of course, is we have independent samples from each of the groups. All right. Something that's a little bit new is we assume equal variances. So this is the idea of using a pooled variance when we're doing a 2-sample t-test. But now we're looking at multiple means. So we're assuming equal variances. And we also have the continuing assumption of normality for the sample means. And this can be achieved through the central limit theorem in large samples, or knowing that the populations are normally distributed. So what we're going to do, let's begin with an example. And so here we're going to look at cuckoo bird eggs. So cuckoo birds lay their eggs in nests of other birds. And when the cuckoo baby hatches, it instinctively will kick out the original eggs and babies. And if the cuckoo is lucky, the mother will raise the cuckoo as if it were her own. And so we're going to ask ourselves this question: do cuckoo bird eggs found in nests of different species differ in size? So I've got some data here. And so we've got 5 different species of birds, and I've recorded the lengths of the eggs in our samples. So here we have some sample data. I've constructed a box plot to kind of look at things. And so here we have a box plot for the 5 species and their egg lengths. So the green line that I have marked is the mean. So you'll notice in some cases it's different than the median. So there appears to be some difference, at least in this one species, if nothing else. Also, here we have some calculations for each of the 5 species. We've got the sample means, the sample standard deviations, and the sample size. And so here I'll make a couple points. Remember, we needed independent samples, so we'll assume we have that. We need equal variances. Well, standard deviations are just the square root of that. And so the rule of thumb that we're going to use, as long as the largest standard deviation is not more than twice the smallest standard deviation, we're going to assume that it's reasonable to assume equal variances and the test will be okay. Another thing we're going to have to assume is that the populations within each species is normally distributed. And I say that because most of the samples here we have are around 15, which is too small for the central limit theorem to guarantee normality for each of the sample means. So we'll need to assume that at least those 4 populations from which we have a small sample follow a normal distribution. The 60, of course, is larger than 30, so whether it's normal for pipits or not, the central limit there would apply and give us normality. So that's just looking at some of the data. So now let's get to going with the test. And so the hypotheses for an ANOVA test, we're testing for a difference in means across k different groups. So we're essentially looking at mu1 equal mu2 all the way up to mu_k. So all the means are equal. The alternative hypothesis, contrary to the null, would be that at least one mean is different than the others. Specifically to our case with the cuckoo birds, we're testing for a difference in mean egg lengths across the 5 species of birds. So we've got mu1 equal mu2 equal mu3 equal mu4 equal mu5, and our alternative would be at least one of those means is different. So looking at the idea of difference in means. So whether or not two means are significantly different depends on two things: the difference between the group means themselves and the variability within each group. And so to illustrate this just a small bit, let's look at this. This would indicate significantly different. And here, the variability between the two group means exceeds the variability within the groups. So because each of the groups has very small variability, then this small difference in means of just one is easily detected versus something that was not significantly different. Here, the variability within the groups exceeds the variability between the two group means. And so in this case, it would be hard to find something that is statistically significant. So if you want to note, if it's significantly different, this is going to generate a fairly large F statistic, where if it's not significantly significant, it will generate a small F statistic. So how we're going to measure this, we're going to be looking at sums of squares. And so here I'm color coding things a little bit. We have the total variability, which looks at the residuals of each value and the overall mean for all eggs in our samples. And we have the variability between groups, which just looks at the mean for each group and how it deviates from the overall mean from all eggs sampled. And the variability within groups is just comparing each individual value within a group to its individual group mean. And so to kind of highlight what we're looking at here, so remember the colors. So the total variability looks like this, where this light blue colored line going up the middle represents the mean over all eggs in all samples. And so we figure out how far away this point is from that. Also looking at this one point, for the variability between groups, we will look at the mean of that group, which are these little green sticks for each of the dot plots, and how far it is away from the overall mean. So this is the variability between, and the variability within the groups is to look at each value and how far away it is from the mean of just that group. And so these are going to have names in the table that we're going to be looking at. And so the total variability will be referred to here as the sum of squares total. And for the variability between groups, we have the sum of squares between the groups. And the variability within groups is referred to as the sum of squares of error. So any analysis that's done using ANOVA and software will usually generate a table that looks something like this. And so you've got different columns for degrees of freedom, sums of squares, something we haven't looked at yet, the mean square, which is just kind of an averaging by dividing by the degrees of freedom, and then the F statistic, which actually is a ratio of the average sums of squares for the groups over the average sum of squares for the error. So we're comparing the variability between groups with respect to the variability within groups. So let's get started. So first of all, the degrees of freedom. So the degrees of freedom for between groups would be the number of groups minus 1, which is 4. And within groups, it's the total number of eggs observed minus the number of categories, which in this case is 115. And then the total degrees of freedom would just be the sum of those two, or the overall number of eggs observed minus 1. Next, we look at the sums of squares. And so using our calculations that we saw previously, we calculate the sum of squares between groups to be 35.899. The sums of squares with the error, 101.289. If you add those two sums of squares, you get the total sums of squares, which is calculated in this manner, which is 127.188. So we've got the degrees of freedom and the sums of squares. We move on to the mean square, which is simply just taking the sums of squares and dividing by the degrees of freedom for each. And so we get 8.977 and 0.811. So then moving to the F statistic, which is just the quotient, the ratio there, we end up with an F statistic of 10.189. And so when we look at this, the greater this F statistic is indicating that the difference between the groups is far greater than the variability between the groups is far greater than the variability within. And this is going to lead us to reject the null hypothesis. If they've been relatively the same, or the mean squares between groups was less than the mean square error, we would tend to not reject. We have a very small F statistic. And so our F statistic actually has 2 degrees of freedom, one for the numerator and one for the denominator. And so if we have an F statistic with the degrees of freedom 4 and 115, we can calculate the p-value as the area beyond the 10.189, which we found to be 0.00000043, very, very small p-value. In that case, we would reject the null hypothesis. And our conclusion would be that there's very strong evidence that the cuckoo bird eggs found in nests of different species actually differ in size. So, to kind of review the process a little bit, I've got this last slide that you can look at in the PowerPoint. Hypothesis test ANOVA, when you have more than 2 population means. We have our hypotheses that all the means are equal, and the alternative would be that at least one is different. Our F statistic is just the mean square between groups over the mean square error. And then the p-value is the probability of witnessing a F value greater than the statistic we calculated. And then our conclusions are based, as is typical for confidence or hypothesis test, that whenever the p-value is small, we reject, and whenever the p-value is large or not small enough, we fail to reject. And on the slide here, I've also included the assumptions we looked at earlier: independent random samples, equal variances, and normality amongst the sample means. So this is just a quick example and review of the process. What I would want to do is look a little bit at how to use StatCrunch to achieve this. So here I've got my data, and I've got 5 groups in 5 columns. If I select Stat and go down to ANOVA, we're looking at a one-way ANOVA. So I'll choose that. Here I just need to highlight the 5 categories. And there's not much really to look at here. So I will just hit Compute. And here you can see, here's the summary data for each individual group. And then down here we have the ANOVA table, in which they've given us the degrees of freedom, the sums of squares, the mean squares, the F statistic, remember we know our statistic, and our p-value was so small that it went off the chart. So in this case, they've just told us it's less than 0.0001, which is consistent with what we found using the F calculator. So if you want a more precise p-value, let me note this. You could go to Stat, go to Calculators, and choose the F calculator. Here we're looking for the probability of being greater than. Now we need to change the degrees of freedom to 4 and 115, as was the case in our problem, and being greater than 10.189. And when we press compute, there's where you get our 0.00000043. Now notice it's so far out in the tail, it doesn't show up graphically. So this is just a quick overview of the ANOVA test with assumptions and how to use StatCrunch to actually get the table along with the F statistic and the p-value.